Hi, we are the CatSats, and this is our final project, including Sophia Fakiri, Lassia Mir, Jessie Wang, David Shi, and Anushka Dole. Here's our table of contents. So for design and plan, our mission is for the CatSat to address coral bleaching by providing scientists with images of the coral reef and its waters. Its geosynchronous orbit allows it to be focused on the Tobata Reef while also being close enough to collect the data needed. When the CubeSat measures the temperature of the water, it measures it to 35 plus, which triggers the camera. When the camera takes the picture of the coral reef, it'll see if there's bleaching and send it back to the ground station. So this is the structure of our CubeSat. We have a camera at the bottom, our battery hanging on the side, a solar panel on the top, and then the Raspberry Pi in the middle.
So for our setup, we have a coral reef, which is represented with a plastic sheet as the water, and then we cut up colorful strips of paper as the live coral and white pieces as bleached coral. The bleached coral was only added once the temperature was high enough, which is representative of actual coral reefs like the Tuba Taha, in which coral bleaches and turns white at high temperatures of water. So our CubeSat was placed over a table over a gap so that the camera was able to take clear photos, but the CubeSat itself didn't move, which is representative of its geosynchronous orbit. The camera was always facing downward towards the coral, and we had a Raspberry Pi and our satellite as the onboard computer. So the Raspberry Pi communicated with the ground station, which consisted of a laptop. We used GitHub for code, and we had a keyboard to type in the temperature. Because we don't actually have a heat sensor, we manually typed in the temperature, which is representative of if we did actually have a thermal sensor to measure the temperature of the water, and that would send a message to a ground station. And it would also trigger a photo from the camera. We have a monitor to display our program, and we had image files from when the camera took images. The bottom left picture is an example of a picture of our coral reef from the camera. So for our setup, we have our ground station operations, which is the left image. And then we have our CubeSat, which is placed over the gap in the table, as I mentioned, which is which simulates geosynchronous orbit. We had on the ground we had our coral reef, which was colorful pieces of paper over a plastic sheet to represent live coral in the ocean. And then we had the bleached coral, which we added once the temperature was above a certain level.
Okay, so this is our ground station operations. So basically, how we communicate with our CubeSat is through the terminal here. And since we don't have a spectrometer, we I coded it so that it'll prompt like the user for like detecting temperature, like simulating the spectrometer. So what it does is basically anything that's under 35 degrees Celsius and put it into here, just won't take a photo. It'll keep repeating until the temperature reaches 35 degrees. And once it's over 35 degrees Celsius, the CubeSat will take a picture and it'll process the image and detect whether there's white in the picture, which will be like the bleaching. So everything will be uploaded to our GitHub and the images will be uploaded into this images folder. And if white's detected, it'll get logged in the images change logs file. So here, you can see like what it'll look like if there is white that's detected. And this is the image that's associated with this white. So you can see like this significant bleaching here. And if that's detected, then it'll upload onto the GitHub.
So for our CubeSat demo, we had our CubeSat above a table looking down a hole onto our coral, which has plastic to simulate the waves, and we put white patches to simulate the coral bleaching. So this is how our code worked. Since we didn't have a spectrometer, we had to make sure that we could put a temperature in. So when we put 34 in, it won't detect or take a picture because it's too low of a temperature. But when it's 36, it'll start to take a picture. Without a spectrometer, we were able to change our code to input a hypothetical temperature to take the picture. We were able to successfully evaluate the photos and detect if there was bleaching, meaning that when we saw in the picture that all three of the RGB values were greater than 200, we would take the picture and send it back to the ground station or our GitHub. And some possible errors are image processing algorithm may not be applicable to the real world, and that could be a cause of the camera resolution.
Hello, I'm Lasia Amre, and I'll be going over key considerations for scaling our CubeSat project to flight software. Our CubeSat is designed to take pictures of coral bleaching, so accuracy and reliability are critical to our mission. As we move towards deployment, there are several aspects that we need to implement and improve. First is calibrating our spectrometer and camera. We will be using an STS UV miniature spectrometer, and to ensure accurate data collection, we need to calibrate it before launch in simulated space conditions. This will help us capture high contrast images with minimal noise, which is essential for detecting coral bleaching. Additionally, optimizing data compression will help us make the most out of our bandwidth. Next, our deployable solar panels are crucial for providing power. We need a controlled deployment sequence, real-time monitoring, and failure detection to make sure they function reliably in orbit. To improve efficiency, we'll implement adaptive power management and maximum power point tracking. And if power demands increase, we'll explore using higher efficiency solar cells as a backup. And onto our cantilever boom, which is a key part of our design. Since we needed to ensure it extends our antenna smoothly without excessive vibrations, we'll need to model its stability and integrate real-time feedback mechanisms to monitor its deployment. And for added security, we'll be including a secondary locking mechanism. And for this, our software will verify that it's engaged before moving forward with other operations. And we'll also have contingency plans in place in case the primary lock fails. Another key component of this is the spring-loaded deployment system, which will need to optimize the string tension and ensure precise control of its timing and sequence. To prevent failures, we'll also implement fail-safes that detect and correct any issues during deployment. Before launch, we'll run rigorous simulations and tests to validate its performance. Oh, this is a picture of our cantilever boom. This is a close-up of our camera and sensor box and how they get protected. Feel free to pause as needed. And because software reliability is just as important as hardware, we'll be designing fail-safe protocols to keep our CubeSat running smoothly. This includes error detection and recovery systems to prevent mission failure, as well as a timer-based reset function to reboot the system if it ever hangs. And we'll also be using an adaptive imaging schedule that adjusts based on the Earth's rotation and the cloud cover to ensure we capture the best images possible. And in space, managing heat is one of the biggest challenges we'll face, especially since our CubeSat will be in a geostationary orbit where it will be exposed to continuous sunlight for long periods. And without the natural cooling effects of Earth's atmosphere, we'll need to carefully regulate temperature to protect sensitive components. To achieve this, we'll integrate radiators that serve as both active and passive thermal regulation systems. These radiators will dissipate excess heat by radiating infrared energy away from the CubeSat. Passive radiators will help manage background heat levels, while active systems can adjust heat dissipation based on real-time temperature readings from our onboard sensors. We'll also be evaluating the use of phase change materials near critical components like the camera and the inertial measurement unit. These materials will absorb and store heat when temperatures rise and release it gradually as temperatures drop. This helps prevent thermal spikes that could affect imaging quality and our sensors' accuracy. We'll also need to plan for the end-of-life disposal of our CubeSat. To minimize its space debris, we'll execute a controlled deorbit strategy once our mission is over. Finally, These are a few key areas we're hoping to improve. First, we will strengthen the frame using aluminum alloy for durability. We'll also be optimizing the battery with radiation-hardened lithium cells for longer operational life. And as reliable communication is essential for CubeSat's mission, we'll need to maintain a stable signal transmission and ensure that our antenna remains structurally sound and properly aligned throughout the mission. First, the antenna must withstand the mechanical stresses of launch and deployment. Any misalignment could weaken the signal strength or cause data loss, and to prevent this, we'll use reinforced mounting structures and secure deployment mechanisms to keep the antenna properly positioned in orbit. Additionally, we'll monitor its alignment with real-time telemetry data to detect and correct any deviations. Another key challenge is radio frequency interference, which can degrade our signal quality. To minimize this risk, we'll conduct RF interference testing to identify potential sources of disruption, whether it's coming from other satellites, Earth-based transmissions, or our own onboard electronics. Shielding techniques and frequency filtering will help us maintain clear communication channels. And by addressing these factors, we'll make sure our CubeSat is not only mission ready, but also reliable and efficient in space.
So next I'm going to talk a bit about how we decided to choose an orbit. So as you know, we did decide to choose a geosynchronous orbit, and some of the characteristics of a geosynchronous orbit are that it's prograde, which means it moves in the same direction as the Earth, and it has a low inclination, which means that the angle variation of the orbit is not that much. And the period of a geosynchronous orbit is approximately 1 day, which means that the satellite is essentially in sync with the Earth as it rotates. So the final characteristic, which I thought was important to highlight, was the fact that there's a constant longitude and that it wanders a bit north to south, but in general, constant longitude. So the two main mission requirements which we wanted to fulfill and that we felt that the geosynchronous orbit would best fulfill were the fact that we needed to be able to measure the temperature of the water. So in order to do that, we had to be close to the Earth. And an orbit close to the Earth, like a geosynchronous orbit, would be within 20 to 30 kilometers from the Earth's surface, which would be close enough to measure temperature. Next, we also need to be able to take photographs of the reef when water is warm. So in order to do that, we would need to stay near the Tabata Reef in terms of location. And because the orbit is in sync with the Earth and it maintains a relatively constant longitude, we would be near the Tabata Reef at all points during our orbit, which would be perfect in order to achieve the two main orbit considerations for our mission. And finally, I'll also be talking a bit about some of the lessons that we learned throughout the CubeSat challenge and also throughout this presentation. So the first issue that we experienced was diagnosing connection issues from the Raspberry Pi to a monitor. So many of us came into this challenge with not much experience with Raspberry Pis and not necessarily being that well versed in software or the hardware that came along with it. But luckily, we were able to work with our mentors and get connected and stay on track with the challenge. The other main thing that I believe we learned was essentially the engineering design process. So learning how to go from brainstorming, mechanical design, to creating a CAD, to creating all the various diagrams that we created throughout the design presentation and the final presentation. That was all very well managed by using Figma, a design software, which each of us learned how to use in order to brainstorm and to create our diagrams and various components for our presentation. Another aspect of engineering which we learned was systems engineering. So we learned how to integrate many different subsystems like hardware and software to work together and create our technical demo. Next, we also learned that going from an MVP to a final design would greatly simplify the development process and make things easier for us in the long run. So breaking up the challenge into a bunch of small pieces, like first tackling the flat sat, really helped us because making the flat sat gave us an overall understanding of the components and it gave us the code base we needed to ultimately create our final challenge code, which saved us a lot of time when it came to the technical demo. And finally, teamwork and delegation is something that we really improved on from the beginning to the end. So at the start, we didn't really know how to work together as a team, but by the end, we were essentially almost working as a unit. So that was great. Thank you so much for listening to our presentation, and I hope you enjoyed.